Oh, yeah, between the marks. You have to stay here.
Oh.
The whole hour. When the next team comes up, we'll just shove you back to schedule.
Sounds good. Won't be able to see Moses. Get a private presentation.
What's that?
Oh, introduce yourself first. Introduce yourself. And let's do that. So lead you.
Well, I think we'll go ahead and get started. We've got 3 teams during this first session, teams 1, 3, and 5, odd, and we'll basically let the students introduce themselves and what their project is about, so you don't hear very much from me. If you see me waving at the team, it's just letting them know how close to being the time's up and stuff like that, so it's not like I'm trying to get their attention. Okay, so team 1, you ready?
Okay. So we are ECE 18.1, and the name of our project is the Energy Conservation Study. My name is Lee Norris.
I'm James Hutlinger.
Kendall Nishina.
And I'm David Dean. The other 2 members of our team include our faculty advisor, Kirk McClurnsberry. He's a project engineer at Tycos Energy, which is a solar developer that is based out of Seattle. And our engineering liaison, David McDonald, who is an engineer at Alderwood Water and Wastewater District, who is also our sponsor. Our sponsor is a special purpose utility that is based out of Linwood, Washington. Their customer base is approximately 250,000 people, and the primary services they provide is water storage and delivery and wastewater removal and treatment. Our project for this year was to determine the technological and economical feasibilities of solar power production at various district properties, and this is also going to include a 30% design for a single property.
Okay, so battery overview. The requirement that we were given is that batteries provide 72 hours of backup power to critical systems, including lighting, SCADA, and chemical injection. As it stands, SCADA has an existing uninterrupted power supply of 13 to 14 hours, whereas lighting and chemical injection do not have a backup source of power. The purpose of adding this backup source is to increase redundancy and to increase safety. For example, adding backup power supply to lighting will ensure that emergency crews can access systems and perform maintenance, as well as deploy generators during grid outages. Given that these batteries will be used as a backup source of power, we are recommending that deep cycle lead acid batteries be used. This is because their characteristics suggest that they perform best when used irregularly. The lifetime of this battery is dependent upon its temperature, age, and number of depth of discharge. Given that these will only be used during maintenance periods, we don't expect the frequency and depth of discharge to significantly affect the battery life. Furthermore, the average battery life of this is 5 to 10 years. And given that we don't expect these factors to significantly reduce it, we think that the battery will last longer than 5 years. So for battery sizing, the dependent factors were site types and critical systems. The critical systems vary based on the type of site that it is. So wastewater sites have both lighting and SCADA, whereas water reservoir sites have lighting, SCADA, and chemical injection. When sizing these batteries, we use 24-volt DC batteries to minimize the number of panels that were required to charge the batteries for 72 hours within one day. So for lighting and SCADA, lighting varies by site, SCADA stays the same by the type of site, and then chemical injection just is applicable to small water reservoir sites.
So at the beginning of the project, one of the first things we had to do was get power information to find out how much power consumption is used at each property. And what we found is that we got data for 29 different meters, and some properties had multiple meters. So the first thing we did is consolidate the meters. So we had a total consumption amount for each site. There was 22 total different properties, and the way we categorized them was 8 of these sites were lift stations, and we classify them as they have limited space for solar power production. 3 of the sites are spaces with minimal space for solar power production solar panel installation, and that includes 2 PRV stations, which is pressure reducing valve stations, and the Mukilteo master meter. The remaining 8 sites we classified as having substantial space for solar power installation. This includes their actual water storage facilities and their wastewater treatment plant.
So in order to perform a cost analysis, we first had to have a comparison of the generation capability and the power consumption at those sites. So first we looked at the consumption and how much energy they used, and we broke that down into 2 categories, the total amount of energy used and how much energy their critical systems used. Once we looked at that, we performed simulations using a program called System Advisory Model to estimate how much energy that those sites could produce from solar. Some of the inputs that SAM required were the type of panel, the type of inverter, how big the system is, or where the location of the sites were to have the solar data. And once we did that, we performed a shading calculator, which would help get an accurate estimation of how much energy could be produced, and then that would show the detailed outputs, like the monthly breakdown of how much energy that is produced from the system or the losses from the system. You can see on the picture on the right, it's the graph of the monthly production. So you can see that the summer months produce way more energy than the winter months. I'll show a little more about the outputs as well later. So as I talked about before with the shading, we had to create a 3D environment of the site to get an accurate estimation of how much shading there would be by the surrounding objects. So some of those objects would be the trees or buildings surrounding the stations. As you can see on the left, it's a 3D model. So all of the green objects are trees. The blue square in the middle is the solar panels that we install. And the red objects are buildings that are surrounding it. And then on the picture of the right shows the Google Maps picture that we could overlay our 3D environment over. And Google Maps helped us to estimate how big those objects were, because we didn't have exact measurements of these objects. And once we completed that, we could get a detailed output. As shown before, we had the monthly breakdown of how much energy could be produced. We also have this graph on the left, shows the solar irradiance that we would have after shading and soiling. As you can see, the summer has the majority of the solar irradiance. On the right shows the total energy loss from the system. And then you can see that shading takes up a little over 50% of that. The rest of the loss from the system is mainly like the conversion from DC to AC or some of the wiring in the system. But yeah, those are some of the detailed graphs we can get from the SAM program.
When installing solar systems, one important variable is the solar incentives. And so the first one we're going to mention is the federal income tax credit, which is actually you're able to receive 30% back on the total cost of each solar system. Unfortunately, because Alderwood Water and Wastewater District is federally tax exempt, they actually are not eligible, but that is the reason why the payback period that you'll see soon is a little lengthier than expected. There's also a sales tax refund. So for 75% of the sales tax you pay for on each solar system, you actually get that refunded back. There's also, Washington State has a unique production incentive. So for residential, it's $5,000 per year, and for commercial, it's $12,000 per year. Or I'm sorry, $25,000 per year. And what makes a commercial system is anything over 12 kilowatts. And this production incentive gets paid for the first 8 years the system is built, and or up till 50% of the price of the system is paid for, whichever one comes first. And then Snohomish PD offers net metering aggregation. So in solar system designs that the solar system designs more than or generates more than 100% of the site's consumption, you'll have an excess of solar credits, and so you can sell those solar credits from that meter to a different meter that may not have additional solar credits for $30 and possibly get some more financial incentive that way. We also contacted solar contractors to get accurate price information on how much solar systems cost for price per watt. Snohomish PUD actually maintains a list of registered solar contractors, and so we contacted more than 10 from this list, and we received feedback from 3 of them, the 3 that are highlighted in orange. We found that the lower end was $2.50 per watt, and the high end was $3.20 per watt. When designing the solar systems, our first approach was to maximize solar generation, and we did this because we thought that the more solar power was generated, the better the payback period would be. For one of the larger sites, their administration building, you can see that it's a fairly large solar system. It's 345 kilowatt system. The cost ranges from $864,000 to $1.1 million, and this is using the low end and the high end estimates, with a payback period of 21 to 29 years. For lift station 17 and PRV station, both those sites actually, we could not design a size big enough to generate 100% of the power's consumption, but they are a lot smaller and they're also a lot cheaper. So for design option 2, our goal was to reduce the system size to reduce the total cost for these systems. And we went off we knew we had 72 hours worth of backup battery, and so we designed the solar systems to charge those 3 days worth of batteries in 1 day. So as you can see, using the administration building as an example, the system goes down drastically down to a 19.8 kilowatt system. The price gets reduced to $49,000 on the low end to $63,000 on the high end, and the payback period is 24 to 33 years. You may have noticed that for lift station 17 and the PRV station, the system size for design option 2 is actually bigger than design option 1, and that's because the site itself doesn't have enough real estate to install enough solar power to have a system that can charge 3 days worth of batteries in 1 day. So this design option needs more refining, but that requires a more thorough analysis for each of the 22 sites, which we did not have time to complete.
So this is our 30% design. The big image is what the existing system that's already there, and below is our design implementation. So to explain each part, the grid will feed electricity. The hybrid inverter charger and ATS stands for automatic transfer switch. This will differentiate the power from the solar power and the grid. So it'll take the solar power electricity first, and then it'll supplement the grid power as needed. The batteries will be charged when they're not in use, and if there's no grid power or solar power available, then the batteries will discharge. Solar power will produce electricity into DC electricity, and then it'll go through an inverter to convert to AC. And then from the hybrid inverter, it'll go to the critical panel, and the critical panel just distributes the electricity to the lighting or to the SCADA. And for reservoir sites, chemical injection will also be there. So during normal operation during the daytime, solar power will be the primary source of power. It'll go through the inverter to the hybrid inverter charger and ATS, and then to the critical panel, and then it'll distribute to its loads. The batteries will be charged by solar if there's an excess amount of solar power, or will be charged by the grid. During night, the grid will be the primary source of power. It'll go to the hybrid inverter charger. The batteries will be charged by the grid, and then it'll go to the critical panel and then to the loads. So during maintenance periods, or if there's a natural disaster that the grid becomes unavailable, solar power will be the main source of energy. Go to the hybrid inverter charger, and then to the critical panel and to its loads. And then the batteries will either charge or discharge if they need to be supplemented. And if there's no grid at night, there's going to be no solar, so batteries will discharge, and then it will feed the SCADA and the lighting panel.
So for our schedule, in the fall quarter, we are primarily focused on researching the 22 properties, so the critical systems that are present at each property, and then the 2016 energy consumption of those loads. And then for winter quarter, we are primarily focused on the analysis and evaluation. So all of our SIM simulations, creating our design options, and so on, were all in winter quarter. And then for spring quarter, we were primarily focused on our final deliverables and fine-tuning our design options.
This table shows our budget over the 2017-2018 year. Majority of it is from transportation, so either parking passes for a liaison or transportation to the Elderwood site. So the total we spent was $117.37. Our original budget had us at $145, so we're under budget.
Any questions?
Hey, so you showed all of your power distribution as being on the AC side of the system. Did you have any DC loads?
So SCADA actually has a AC and DC inputs, and the hybrid inverter can also output DC as well.
So you presented the payback period, and I'm wondering if that is that just based on solely energy, or is there some sort of valuation for the improved safety and redundancy that's included in that?
So the payback period, the variables that go into that are the amount of power that they're not paying so much PUD, what they're getting from the production incentive, and that's it. So those are the two things so for the cost of that specific system, how long it takes for that system to pay for itself, those are the things we considered for the payback period.
Did that initial cost include the credits?
So design option 1, there's a possibility of getting credits, but in regards to like the net metering aggregation, if you have extra credits, it's hard to actually put a number to how much that they would actually generate extra, because every month's a little different, and we used what they used in 2016, and so we size the systems for the amount of energy that they consumed in 2016. So we don't actually know how many credits they would have, so it was hard to put a number to it, so we didn't use that. So it would actually probably be slightly better, but probably not significant enough to see years come off of the payback period. Yes, sir.
Why did you choose to run the solar DC through an inverter to your transfer switch rather than floating directly to the battery?
We kind of centralized the hybrid inverter for everything to run off that, to be more simple. And also, our scope was more high level, and more thorough analysis at a site specifically can get the connections where exactly they need to connect.
I had a question. On the cost for a design option 2 for, the batteries, just doing lighting and so forth, did the cost include replacement of the batteries every 10 years or so?
So the payback periods you saw was just for the solar system only. We actually have different pricing information for the batteries that's included in a different appendix, actually, if you wanted to see it. But yeah, the payback period is just how much does the solar system take, or how many years does it take for the solar system to pay for the solar system.
Okay.
So, yes, sir.
What did you use for the solar installation numbers? In other words, obviously December, November, solar power is a lot less than in summer. So when you looked at your payback period, how did you figure out how much solar you're actually going to be generating? How much power you're going to actually be generating from solar?
Right. So our program SAM, System Advisor Model, that actually did show us how much is generated throughout the year, and the systems that are sized to provide power for 100% of the site, they would have a lot of excess generation in the summer, so those credits would be distributed over the winter months, kind of thing. And so, in the end, if it was 100%, if the system was designed for 100% of the consumption, they wouldn't actually pay anything to so much PUD, because the credits would end up paying for your grid power that you're using, since you're not generating enough solar in the winter months.
Any more questions? Okay, thank you very much.
Hello everyone, we are Team ECE 18.3 and our project is Hydroelectric Generator Capability and Protection Coordination Model. My name is Salman Liami.
I'm Emily Boss. I'm Jeffrey Ng.
And I'm Han Tran.
And our sponsor is Chelan County PUD. Our project liaison is John Yale. He's a hydro plant engineer manager at Chelan County PUD. Our faculty advisor is Paul Kostick. He's a senior system engineer at Base 2 Solutions. Chelan County PUD is located in the beautiful Wenatchee of Washington.
A little bit more about Chelan County PUD is that they produce 9 million megawatt hours of energy a year. They own and operate 3 hydroelectric dams. One of the dams is Lake Chelan Dam with 2 generators with a capacity of 59 megawatts. Rock Island Dam has 19 generators with a capacity of 624 megawatts. And Rocky Reach Dam has 11 generators with a capacity of 1,300 megawatts. They are generation rich with a total approximate capacity of 2,000 megawatts.
So a little bit of an overview about our project. We were to develop a tool to model generator capability curves, voltage regulator capability, operating limits, excitation limiters, protection limiters, and protective functions. Our tool, our project was supposed to prove that Chelan County PUD is actually in compliance with the North American Electric Reliability Corporation, NERC, standards PRC 019 and MOD 025.
In 2003, there was an event called the Northeast Blackout that triggered NERC to be produced. So this event caused 50 million people to lose power for about 48 hours in both the United States and North America. And because of this, billions of dollars in damages occurred and 100 lives were lost. And that is where NERC came in, the North American Electric Reliability Corporation, came in with sets of standards and regulations for generator owners to operate and regulate. And that is where our 2 standards of PRC 019 and MOD 025 comes in.
So there were some specifications to our project that we were required to meet by Chelan County PUD. First of all, our tool must be universal, which means that it must work on all of Chelan County PUD salient pole generators. Also, it must be implemented in Microsoft Excel, and that is due to the fact that that's the program that the engineers at Chelan County PUD have access to. Also, it must be modeled in the PQ plane, which is the apparent power plane, instead of the RX plane, which is the impedance plane, and must be expressed in per unit. Our model should include protection and capability curves required from NERC standards, again, PRC 019 and MOD 025. We're also required to add transformer volts per hertz limits, and that is different from the generator volts per hertz limit. And lastly, we're required to add minimum and maximum real and reactive power test points to our tool. Our solution to that was creating the generator compliance coordination tool, the GCCT.
In order for us to build a tool to help protect generators, we needed to know what we were protecting. Here's this little overview of how a hydroelectric generator works. Water comes from behind the dam through the yellow wicket gates and rotates the turbine in red. As the turbine rotates, so does a rotor because it's connected by the turbine shaft. The rotor is an electromagnet that's housed within the stator. And by the principles of electromagnetism, we know that a change in magnetic field could cause current to flow through a wire. So the rotor provides our magnetic field, and the windings around the stator carry the current that is induced to the transmission and distribution system.
The generator capability curves make up the safe operating regions of a generator. The armature winding heating limit corresponds to a heating limit for the coils in the stator. Likewise, the field winding heating limit corresponds to the coils in the rotor. And lastly, the steady state stability limit corresponds to the physical components of the generator. It will protect the generator from losing synchronism with the grid or even slipping a pole. And these 3 curves here make up the generator capability curve.
Aside from the 3 generator capability curves, our tool needed to be able to plot these other things. The over-excitation and under-excitation limiters prevent the generator from operating too close to the field winding heating limit and the steady state stability limit. Protection functions can activate if excitation systems fail. Over and under voltage protection can activate when a sudden load interchange occurs and the voltage spikes up or dips too low. Loss of field protection activates if the under excitation system fails and the stator and rotor lose synchronism with each other. volts per hertz monitors the voltage and the frequency of the output and make sure that it stays the ratio stays the same. Finally, our tool is able to plot the minimum and maximum real and reactive power capability test points, which represent the power capability of the generator when it's running or based off a test done by Chelan County PUD. Here's an example of a coordination that might be done with our tool. You have the field winding heating hit limit in blue, and that is a physical property of the generator. So we can coordinate the overexcitation in gray to be slightly underneath because it limits the operating region of the generator. And if that overexcitation limit fails, we have a overvoltage limit in red, which prevents the generator from operating at high voltage for too long.
So the GCCT is implemented in the PQ plane, which is the apparent power plane. However, some devices' characteristics are actually implemented in the RX plane, which is the impedance plane. For example, loss of field for the generator is implemented with distance relays, and those are activated based on the measure of impedance. If we see on the left, the two green circles are actually the two zones of the loss of field for a generator. Those are in the RX plane, and we can see that they are just two simple circuits. However, when we did the conversion to the PQ plane, the shape is different, and we can see that as the two curves in the bottom of the PQ plane. We have to point out that coordination can be done on both of the planes, whether the RX or the PQ. However, since Chelan County PUD have specifically asked us to actually implement it in the PQ plane, we had to do the conversion.
Another thing we had to consider was when plotting the transformer volts per hertz limit, the GCCT needs to be expressed in per unit with respect to the generator base. And so when we consider transformer protection, we need to be able to translate the transformer rating with respect to the generator base. To do this, we look at some data provided by Chelan County. If you zoom in, you can see a column for bank MVA, and that's the rating we'd be using. There are 4 values in it, which correspond to the different cooling stages in the transformer. If you look at the last value in there, 152 MVA is the transformer rating when it is operating at 65 degrees Celsius. This is the rating we'll be using because when we're talking about limits, you want the greatest known rating of the transformer. After this, we can calculate the transformer rating with respect to the generator base to be 1.0 per unit for this value. And with that, we can plot the transformer volts per hertz limit the same way we can plot the generator volts per hertz limit.
Now we can move into a demonstration of the GCCT. So on the left is our generator book values. This is values that the engineers at Chelan County will have access to. On the right is the GCCT. The parameter sheet will be acting as a home page for the GCCT, and this is where we'll spend most of our time. We want to start by entering who's doing the coordination, as well as the date. We'll just go down the line and fill these things out, so we're going to be using unit C8. And then finally, we will also have the ability to turn curves on or off using those toggle methods. You just check on or off, and then once you have filled out all of this information, you just press graph generator capability curve, and it'll plot your output. We also have implemented some protection functions in this document to help make the coordination easier for the generators, or for the engineers, sorry. So if they are wanting to enter a parameter and it's outside of the scope of a reasonable number, it'll send up an error message essentially saying, hey, that's out of the range, enter something within this range, and it's more likely just to prevent unreasonable errors. As well, we have protected parts of this document to protect the integrity of the document so that they can send an intern in there and not mess up anything too poorly.
So when we talked about verifying our GCCT to see actually if it's accurate, there are 2 different ways that we decided to verify. One of the ways we decided to verify is to look at Chelan County PUD's coordination. And as you can see, there are many types of curves that are on there which are outside of the scope of our project. But we looked at the generator capability curves, so the armature winding heating limit, the field winding heating limit. We also decided to look at the generator manufacturing data, and once again looked at the generator manufacturing, generator capability curves. But we looked at the general shape, but we wanted to dive in deeper and look at the specific points of intersection rather than just saying they looked okay.
The specific points Hunt is talking about are our intersection points. So with our armature winding heating limit, it is a unity circle. So long as it is centered at 0 and has a radius of 1, it's looking good. So we looked at our field winding intercept with the armature winding, and that should intercept at the machine's rated power factor, which is 0.95. And in all of these cases, it did. So we were able to move on from that. We also looked at the reactive power axis interception, and this is where we had most of our variation in our verification. We were able to determine that this was due to ours are theoretical calculations where the generator manufacturer is practical applications. And so we also did that with the steady state stability limit. We looked at its intersection with the armature winding heating limit. We were aiming for 5% error with all of these, and we were able to meet that tenfold.
In fall quarter, we focused on researching all of these types of curves and understanding what they actually meant, as well as writing our written proposal. In winter quarter, we focused most of our time onto actually implementing them into the GCCT, as well as verifying our data. And then in spring quarter, we finished up any loose ends that we had, developed the user interface, as well as prepare for final presentations.
As for the budget, we only spent money on travel. Chelan County PUD is approximately 300 miles away from Seattle University, and we made a visit back in fall quarter. So we spent $214.79 on miles and food to and from Chelan County PUD. So in conclusion, the GCCT plots generator capability curves, protection functions, and limiters. Also, the GCCT produces curves within an acceptable range. Are there any questions?
Never ask questions, there's going to be an online quiz. But if you pass, you can be a power engineer.
So on your theoretical calculations versus your actual, what the generator actually did, or what the manufacturer's calculation were, did you ever come to an analysis of what caused that error in the difference? Or, I mean, that'd be one question. The second follow-on to that would be, was there a way, instead of using your theoretical calculations, to take the generator manufacturer's data and then model that and then use that instead of the theoretical calculations?
Yeah, so what we actually ended up doing was using those theoretical calculations, but ours ended up being more conservative. So we felt that that was sufficient, essentially, in accommodating for the difference there. The way that the protection functions work, it would make it okay, essentially, that the difference was there.
Dr. Louis?
Dr. Louis?
Yeah, hi, Dr. Louis. Yeah, could you talk a little bit more about the documentation and the training aspects of your work?
Yeah, absolutely. We actually have provided a project report that was necessary, but within that project report, we put instructions as well as detailed information where the curves were derived from, how they were actually implemented in Excel, what the actual equation looked like. As well, we will be providing, we have a video, we have not handed it off yet, of a video tutorial, essentially, to make it easier if they just want to read a video.
And the GCCT is expandable because the number of protection functions are not finite on a generator. So in that tutorial that, the documentation that Emily mentioned, there is documentation on how to add a new curve specific, like if it's an overvoltage protection or a limiter or something like that.
Rich?
So can you talk a little bit about how you tested your model once you built it?
Yeah, we essentially tested it to the two different curves. So we had a Chelan County PUD coordination, and then we also had the generator manufacturer's coordination. So we were looking at the specific curves. Yeah, pop up there. Yeah, so we were comparing them here. So we were looking at specific points. Since the lines are continuous, we really just needed to test two. We were aiming for 5% accuracy. Like I mentioned, with the field winding heating limit and the armature winding heating limit, their intersection, it should be at the machine's rated power factor. So we had very, very little change there. But what was different was our reactive power axis, and that was what I was talking about with the theoretical versus the practical. And then we did similarly for the steady state stability limit. Now, most of our curves, with exception to the loss of field zones 1 and 2, are stemmed from the generator capability curves. So once we verified those, all of the others are just varying magnitudes of those curves. So we could pretty well assume their accuracy.
And we chose 5% accuracy because when reading through a bunch of NERC recommendations, they actually recommend to coordinate plus or minus 5%. So we thought that in order to allow coordination, we should be at least at 5%.
So you only tested 2 points, right? So is that because you only care about 2 points?
Oh, no, so the curves themselves are continuous. So they're just big circles, essentially.
So did you run those out, though, so you tested the chord to match, so you didn't, have, like, the 2 points end up matched, but the middle doesn't match?
Yes, they're just complete circles. So yes, we did.
So if you were trying to create a tool for compliance with these new NERC standards, how did you get access to the standards to read them?
We actually found them online, but we also use John, our sponsor, and asked them for any information with the 2 NERC standards. But they're pretty much, you can find them online. Yeah, they're national.
Any more questions? Okay, thank you.
Good morning or good afternoon. We're team ECE 18.5, and we are building a Raspberry Pi data acquisition system. I'm Kevin Dow.
Max Singh.
Carrie Smith. Tom Chan. And our faculty advisor is Pierre Deinhauer, and our professional liaison was Dave Goldsmith.
So I want everybody in this room to take a second and reflect back on how important electricity is to your life, to your daily life. Now, there are 1.2 billion people in the world that don't have access to any sort of electricity. They don't have access to proper healthcare, proper education, and just general daily lives. How different would your life be if you didn't have access to any of that? Would you be the same person that you are today? And that's why KWH, our sponsor, Kilowatts for Humanity, is important, because Kilowatts for Humanity was founded by Dr. Henry Louis, Jen Isaacson, and Steve Zalbia. Since 2009, they have been setting up these small microgrid systems in remote locations around the world, countries like Zambia, Philippines, Kenya, and they have been making a huge difference by connecting people that don't have access.
So KWH implements microgrid projects all over places in Africa and other remote locations, and they currently use a King Pigeon data logger. And with this King Pigeon data logger, it's off the shelf, so there are many proprietary limitations that restrict the organization from the data that they can collect. And so we were tasked with replacing this King Pigeon data logger with a Raspberry Pi-based data logger. And so our data logger, it's state-of-the-art, and it serves as the heart and brain of the data acquisition system. It improves the sustainability of the power system, as well as it's a lot more cost-efficient than the King Pigeon data logger. It's able to save the organization money long-term. It's also able to replicate the functionality of the current King Pigeon data logger and extend the functionality. It also allows the organization with more flexibility in obtaining and monitoring data.
So this is a system design overview. This is a typical implementation of a microgrid system, and Mac will be pointing along with our test bench as I talk you through our block diagram here. The sun serves as a solar resource, which feeds into the PV panel, which feeds into the maximum power point tracker, which just optimizes that energy. And that's output into the battery. It's a 12-volt DC, which is then inverted to 220 at 50 hertz. And this is where our part of the project comes into play. So we designed the analog to digital converter. We monitored the current with these two current transducers. And we made a voltage divider to power that analog to digital conversion to step down that voltage to the appropriate level. The Modbus energy meters and the GSM module, which is responsible for uploading and downloading text messages, and the temperature sensors all are communicating with the Raspberry Pi.
So for this project, we had many different components, software and hardware. And one of the main focuses of our project was to make sure that we can sustain this project over time and also the cost associated with deploying certain components. So what we ended up doing was using as much open source software or components that we can possibly use. So for our PCB design specifically, we used a software called KiCad, and it's open source software anybody can download from here. And we used it to create our schematics and also our PCB. And like Hong said earlier, one of the things that we wanted to ensure was that the King Pigeons, the legacy data loggers capabilities were intact, or at least carried over into our system. So we did that by essentially almost everything, and also added other functionalities such as the Modbus capabilities and also the temp sensor bus, so we can actually connect a lot more sensors now.
So one of the other hardware aspects of our project was the enclosure design. So we researched into two enclosures. First, the inner enclosure, which houses the Raspberry Pi, the printed circuit board, as well as the battery, which is shown in the upper right corner. And then an outer enclosure, which encloses the inner enclosure, as well as the King Pigeon data logger, power supplies, and a voltage divider. And so the inner enclosure we looked at had an international protection marking of 67, and the outer enclosure was rated at IP66. So the first digit in the IP rating is the degrees of protection against foreign bodies, and the second digit is the degrees of protection against liquids. And so both of our enclosures are dust tight and water resistant. Another hardware aspect of our project was the antennas. So we started out the year with 3 antennas. We had 2 Yagi-Uda antennas and 1 parabolic grid antenna. And then from there, we performed horizontal and vertical tests on the antennas to see how signal perpetrates and which one had the best signal strength at various degrees and through various objects. And we found that the XL wireless parabolic grid antenna had the best performance. And the antenna is a crucial part of our design because it allows for data transmission to the KWH server. We're able to transmit data on our temperature sensors, our current transducers, pyranometers, data channels, as well as the Modbus energy meter data. And the antenna overall allows the organization to have better signal for remote control and monitoring within our system.
So one of the biggest aspects of this project is to ensure that we can at least preserve the basic functionality of the proprietary data logger that was used before. So our Raspberry Pi data logger needed to utilize the temperature sensors in the same fashion. So we had to put them next to each other, the King Pigeon, which is the legacy data logger, and our new Raspberry Pi data logger, and attach temperature sensors to both of those and make sure that they could have the same data so we could show that the basic functionality was preserved. So the first part of that development was the bottom layer here, the hardware development. We wanted to make sure that they had unique IDs so that when we could use the software to see which part of the load we were measuring. So if it was a refrigerator, we want to be able to know that by the ID of the temperature sensor itself. We were pleasantly surprised to find out that they do have unique IDs and they're fixed. We also needed to make sure that we could implement 3 temperature sensors. A previous limitation of the KP data logger was it would only allow 2. So that's very restricting when you're trying to measure the temperature of several different loads. The next layer is the software development in the center. We needed to make sure that we could receive the data appropriately and that it would be continuous and that we could transmit that data to the KWH serving Grafana website. We were able to do that. Here's a picture of the streaming data for one of the temperature sensors and as an example. And you can see it has the continuous data there. So we found the unique and fixed 64-bit serial numbers, and they were, we utilized one-wire communication protocol. So when we unplugged the temperature sensor and plugged it back in, they dynamically updated. And so we could tell which temperature sensor was where and how many were plugged in. So one of the biggest pushes also for our project is that it's cost efficient and that it's open source. So we use the Raspberry Pi for those reasons, and we use the Raspbian operating system so that everyone can download that for free if they have the appropriate access. We wrote an installer and configuration script so that we could personalize these projects. So basically, if you have any kind of power system that has sensors and you have some sort of data acquisition capability, you can install our script and we can set the port number for you, we can set the website for you that you want to stream the data from. It has all of that available to you and customizable to you. We also, every time we make a change on our GitHub repository for that source code, you can run a command and it will also pull those updates for you, so you can always stay updated and you can always stay continuous. Lastly, we have data management on the Raspberry Pi, where the King Pigeon, we weren't able to really get into the software and change everything because it was proprietary. So that's a big win for us, having flexibility, and we were able to update the time and the date daily and upon booting.
So our system is going to be deployed somewhere remote, possibly with no access to Ethernet cables or Wi-Fi. So the Raspberry Pi itself can only communicate to the outer world with Ethernet or Wi-Fi that's available in the area. And we needed to find an alternate, solution and kind of follow the legacy data logger, right? So what we did was actually used a component called semi-800L surface mount chip, which allows the Raspberry Pi to essentially turn into a cellular device, and it can transmit voice, SMS, and data. And so any of your SMS or your SIM cards from your regular phones can be actually used to insert into this chip, and it can turn into a cellular device. And that's what we were able to do. And the reason we actually selected this chip was because of its size. Like, as you can see, it needed to kind of fit inside the really small box, and it was, so we had to take that into consideration. And also, we can directly attach the antenna onto this component itself, so win-win.
So as Mac was mentioning before, one of our primary focuses was the GSM module's ability to download and upload SMS or text messages. We use those text messages to send and receive what are called attention commands. We call them AT commands. It's just like, hey, modem, do this thing, or I want to know this thing about the system. And so with doing those, we not only preserve the basic functionality of the King Pigeon, which is some evidence right here. This is King Pigeon language for changing the port number. This is sent from my cell phone to our Raspberry Pi data logger. The data logger downloaded the message, processed it, and then sent a nice message back to me saying, congratulations, your port was set to this number. But GIP is a little bit like, what does that mean, right? So that's King Pigeon language. So for the Raspberry Pi, we're able to get in there and actually change it to something that's more meaningful, especially people who don't want to deal with the software behind the scenes. They just want to know, what am I changing? So that was a big win for us.
And so for our meters, we're using Modbus energy meters, and so they measure all the AC data points. as listed above, those are the points that are being measured by the meter themselves. And so these meters run on RS-485 communication, which is an electrical interface used for long distance transmission. And so they use serial communication and follow the master-slave arrangement, where the Raspberry Pi is the master querying the data from the slave, which is the meters. And so for our software, we're using a Python library called Minimal Modbus. And so this module allows for communication, Modbus protocol communication. And so there's two formats. There's RTU and ASCII. RTU is binary, and ASCII is like hexadecimal. And so in our case, we're using RTU. And this module is supported on Windows, OS X, and Linux. And we're using Linux in our case for the Raspberry Pi. Specifically, we're using the function called readFloat, which has 3 parameters: the register address, which is the address of the Modbus, the function code, which is the data point that you're querying, and the number of registers, which is 2 for these meters. So what happens is that the Raspberry Pi queries the Modbus with the function readFloat, and in return, the Modbus will send the data point back to the Raspberry Pi, and that is processed on the Pi and then sent to the Grafana website that we're sending data to. So this is a snippet of our data points collected. Up here you have the AC voltage, the current, frequency, and phase angle. And so this is plotted in real time, as you can see on the bottom axis. And the areas that are blacked out either mean that the system is off or the meters themselves are disconnected. And then so once you plug it back in, data just starts flowing back in automatically.
And so as we've kind of listed out the software and the hardware components, and one of the big things was to have enough time to actually test our overall system. So we conducted a 2-week testing period, essentially, where we turned everything on into the system and just let it run for 14 days straight. And every morning and night, we went and essentially noted down the data point to just make sure that the data that we're receiving is somewhat similar between the Raspberry Pi and the King Pigeon itself. And so we were able to complete all these tests listed. And for future reference, when this system is going to be implemented, we also created essentially a future test suite where the organization, KWH, will be able to follow our instructions to test this enclosure and essentially test these and make sure that this is the system that they're implementing is suitable for the environment and it can work. Next slide. And so the results. So the results, as Kevin mentioned earlier, are actually plotted on this website right here, kwhstg.org, and this is basically like a pilot website where we implement all our data, and all this information's there. And the idea here was to make sure that the Raspberry Pi and the King Pigeon data can run in parallel, so we can actually see the difference between the data points and see that the accuracy of the data points that we're actually receiving. And if they're off, we can actually do something about it. And we were successfully able to do that.
And so for our budget, we were started off with $1,500. And so for our entire year, we spent about $1,400 building this system. And for the data logger, or for the Raspberry Pi data logger itself, it costs around $133 in comparison to the $220 for just the King Pigeon by itself. And so that is a huge difference in cost, and hopefully will be very, very useful for the future. So some of the final deliverables for KWH is the testing suite data that we have collected, the installation packet that has all these listed items in there, and then lastly the bill of materials. One is the overall system, so all $1,400 worth, and then just the deployable Raspberry Pi, which will just be the smaller data logger in here.
We're very excited that we've been so successful in our project this year. When we first put the project into play, we weren't sure if we'd be able to get the Modbus up and running, but with doing so, we have 15 additional data points that we can use to test the technical health and wellness of the system, which should serve us very well in the future, as well as the cost reduction, the significant cost reduction. So thank you. Any questions?
So is there any calibration necessary on a new system, to like account for the sensors or the variation in the resistors and the voltage divider?
No. So there's no calibration for the CTs or the Modbus or the temperature sensors. The voltage dividers are already soldered in already. So those do not need to be changed. And same for the King Pigeon as well. The only thing that needs to be changed appropriately is the configuration for the Raspberry Pi to sending it to the proper like ports. So for example, we have 2 of them running right now. One's the Seattle one, which is ours, and then Denver, which is the one our liaison has. And so they have different port numbers. So those will need to be changed appropriately.
So is it a completely sealed enclosure? And if so, how do you dissipate the heat?
Yeah, so there is a future heat test in there to make sure that we wouldn't have any thermal runaway or any issues with the with that scenario. We have a detailed testing suite with a threshold. If that detailed testing suite does come back with, oh, we made it over the threshold of what's acceptable, we've made our PCB to have open space for a heat sink just in case.
So if you have a complete failure, you just replace the component, or do you have to replace the whole module?
The components are soldered in, so we can, if the components are removable that have been damaged, then we can go that route. But these are going to be implanted in places where people don't have necessarily technical background, so it might take some time and energy and money to do that.
Just a clarifying question. Are you asking about the data logger itself or just the overall components in the system? Okay, so some of the components are bought pre-made. For example, our power supply is by a company called Syncon. And so we wanted to pick vendors that would be more reputable, so that in case that the power supply were to fail, we would be able to buy a new one. Actually, more recently, I accidentally blew up the power supply by accidentally shorting it on the very bottom. But luckily, the components on here are just soldered, so we can replace them easily as well. For the data logger themselves, all the components are soldered on or have a surface mount, so they can be replaced very easily. The only problem that could occur is, like, for example, the PC board is damaged in some way, then the whole component board has to be replaced.
So I have a question about the Modbus sensor. You guys seem really proud of that. What does that do that the existing AC sensors didn't do?
First of all, we didn't even have any way of actually measuring the AC side before this project. So the Modbus actually allows us to measure, like I think Carrie mentioned, several different data points, like power factor, frequency,
energy consumption.
Power factor, yeah.
Yeah, so we have previously what the system has used is these transducers, current transducers right here. And basically, we've been using these to figure out the DC side and guessing the AC side of the system. But now we will actually be sure about what the system is doing on the AC side, and that's a huge win.
And that combined with the AT commands that we're able to send, we can remotely fix a problem or mitigate a problem before it gets out of hand.
So a little bit more about like the data points being collected. Other than like voltage and current, they also have apparent power, reactive energy, and yeah, more data points basically about energy and power consumption, which will help determine, like, let's say for example, different loads that are on the system. So you can see that within the phase angle or like the reactive power and so forth.
And all that information is available on the website as well.
I think we have time for one more question.
but it's clearly, so the only thing we need to do is just order these components. And I think we passed around the PCB board. That was probably the longest, and that takes about 2 weeks. So we should be able to just put everything together and then.
So once you get all the components, we spent about a week and a half building the whole thing. That's with all the parts in already. But ordering wise, it'd be best to plan it out so that everything kind of comes at the same time. We ordered our parts kind of spread out. And so our PCBs, for example, took a week?
Like 2 weeks.
2 weeks.
Yeah.
So accounting for that ahead of time would be advisable.
We also have documentation of sort of our lessons learned, so it would be much quicker for whoever embarks on this next time.